Morning, students. In last class, we have discussed about congestion and congestion principles and two types of congestion mechanisms, that is open loop congestion control and closed loop congestion control. After that, we have discussed two different congestion control algorithms, that is leaky bucket algorithm, and second one is token bucket algorithm. Okay, and after that, we have discussed lastly, we have discussed differences between the leaky bucket and token bucket algorithms. Now, in today's class, we are going to discuss about the topics, what is traffic throttling and choke packets already we have discussed, and explicit congestion notification and hop by hop back pressure also we have discussed. After that, we have to discuss about load shedding. Let's move on to the today's class. Coming to the traffic throttling, in the internet and many other computer networks, senders adjust their transmission to send as much as traffic as the network can readily to deliver. Okay, normally the users are using data to be transmitted and the transmission to be sent as much as traffic, because as they increase the transmission, traffic also increases. In this setting, the network mainly aims to operate just before onset of congestion. That means just before onset of congestion means before the congestion occurs, the network the network is mainly to operate, aims to operate is nothing but the network aims to deliver the transmitted data. Okay, that is before the congestion occurred. When the congestion is imminent, that is imminent means very close. When the congestion is imminent, it must tell the senders throttle back their transmissions and slow down. That means when we know the congestion is imminent, that means congestion is very close, then it must tell the senders to slow down their transmission and throttle back. Throttle back means that is take back, and throttle back their transmission is nothing but the senders can the sender can slow down its transmission. Okay, it can't further transmit the data because the congestion is imminent. Here we are approaching, there are some approaches to throttle traffic that can be used in both datagram networks and virtual networks. Virtual circuit network means that is connection oriented networks. Datagram networks mean that is connectionless networks. We have some approaches. Let's see. Each approach is having two problems. The first problem is the routers must determine when the congestion is approaching, ideally before it has arrived. That means what I told you, before congestion occurs, who needs to identify very soon the congestion may occur, the router may identify. So the routers must determine when congestion is approaching and ideally before it has arrived. That means before the congestion has been arrived. To do so, each router can continuously monitor the resource it is using. Okay, here each router continuously monitoring the resources. The possibilities are the utilization of output links, how the router is utilizing the outputs, the buffering of queued packets inside the router, and the number of packets that are lost due to insufficient buffering. First possibility is by buffering of queued packets. For each router, there will be a queue before entering it. Buffering of queued packets, that is the first one. And the number of packets lost due to insufficient. There is no buffer space. What they will be do? The number of packets are lost because there is no buffer space. And the third one is the utilization of output links. These three are the possibilities of causing the congestion. These three possibilities must be watched by the router. Okay, if these three possibilities are watched by the router, it can identify. okay, when the congestion may causes. The second approach is averages of utilization. Averages of utilization do not directly account for the burstiness of most traffic. Utilization of 50% may be low for smooth traffic. See, we have a output line. See, we have a output line. If we use that output line 100%, there might be a possibility because the utilization leads to a traffic. If we use a 50%, it lows down the traffic and highly variable traffic. That means don't use 100% of outgoing lines. Only if you use 50% of the output line, then there is a very large use variable in traffic. Okay. Second one is the queuing delay inside the routers directly captures any congestion experienced with the packets. Here, the queuing delay is nothing but suppose a packet enters into the queue at the router. The delay is very high. Not what it will do, it will take more time to enter to the router. So that also leads to congestion. These two principles needs to watch by the router. To maintain a good estimate of queuing delay, D, queuing delay is D. To maintain a good estimate of queuing delay D, a sample of instantaneous queue length S. The queue length is containing the packets. The length is S. The delay is D. Can be made periodically and D updated according to D means delay updated according to D new. That is the new delay is AD old plus 1 minus A into S, where constant A determines how fast the router forgets the recent history. This is called as EWMA. That is exponentially weighted moving average. Just you don't but it just to remember the formula. D new is new delay equal to A D old. D old means old delay plus 1 minus A into S, where A is the A determines how fast the router forgets its recent history. Next point. Smooths out fluctuations and is equivalent to a low pass filter. Whenever D moves above the threshold means we have some threshold point. The delay will, if we have more delay, that leads to congestion. If D moves above the threshold point, the router notes the onset of congestion. Simply, what this slide is telling us is, if the delay D is very high at the router to enter the packets, it has some threshold point. The delay is above the threshold point, then the router may expect there is a onset of congestion. That means there is an imminent of congestion, and very soon there will be a possibility of congestion at the router. Second problem is that the routers must deliver timely feedback to the senders that are causing the congestion. I already told you, whenever the congestion occurs at the router, the routers are intimated to the senders to slow down its transmission. See, to deliver the feedback, the router must identify the appropriate senders. From which sender there is causing congestion. Okay, of those senders, it must warn them carefully to slow down its transmission. Without sending many more packets into the already congested network. Why the router is warning to the sender is nothing but already because of sender's transmission, already congestion is occurred. If he sends more packets, what happens? If he sends more packets to the congested network, it will be uh, increasing of congestion. Okay, that is the reason why the router is warning to the sender. Next, different schemes use this feedback mechanism. Who feedback means who are giving the feedback? Feedback is given by the router. The feedback is sent to the sender. The feedback will be like first one, choke packets we have already seen, already discussed. Second one is explicit congestion notification. Third one, hop by hop back pressing. Okay, we have seen choke packets. See here, this is the choke packet approach. In the last class, we have seen this approach. See here, wherever the congestion occurs, from that point, wherever the congestion occurs, see these are 1, 2, 3 Roman letters, 1, 2, 3, 4 are routers. Congestion occurs at this router. From this point, it will directly sends information by choke packet. Okay. If the sender receives the choke packet from the router, the sender will slow down its transmission. This is one way of giving feedback by a router to the sender. Next. Next one is explicit congestion notification. Okay. In the choke packet approach, we need to generate a packet, and we need to use that packet to warn the sender, right? Instead of generating additional packets to warn of congestion, a router can tag any packet it forwards. Router can tag any packet it forwards to signal that is experiencing the congestion. Just what it will do is simply it can tag any packet the router is forwarding. When the network delivers the packet, the destination can note that there is a congestion and inform the sender. See, simply, I will explain this one is very clearly, very in the easy manner. You are receiver, I am sender. In between sender and receiver, we have some routers. Okay, we have some router R. I am a sender. I sent a packet to router R. Okay, already router R finds congestion. Okay, instead of generating a new packet and giving a warning to me, what they will do is the packet needs to be forwarded to destination. That is for you, right? For the packet, what they will tag some information. They will tag some congestion information and forwards that packet to you. Okay. After you received the packet, you will find there is a congestion in the network. Okay. After receiving that packet, that is having some tagged information which is given by the router, right? Just after receiving that tagged information from the packet, you notify to the sender, that is to me, there is a congestion. Okay, just you drop down, you slow down its your transmission. Okay, this is another way of giving feedback. Here, the feedback is given by not router. The feedback is given by the receiver or destination. That feedback information is added by using a tag that will be given by a router. Here, the sender can then throttle its transmission as before. Throttle is nothing but slow down its transmission. Here, the design is called as ECN. It is explicit congestion notification. Okay. See here. This is the picture of congestion. See here. Is host, and that means let us assume this is a sending host and this is a receiving host, and between we are having some routers. This is where my finding mouse is router. Here router and router. See here, this is normal router because only one packet is passing to the router. Here there is no congestion. This is the congested router. This is the congested router. See, to this congested router, see these number of 1, 2, 3, 4 packets are passing. What this router did is this router marked this packet which is bubbled here, they marked this packet and tagged the information of congestion and forwarded to next one. Okay. it passes through the next router and it passes through the, this is the marked packet, and it will reaches to the receiver. Okay. After receiving the marked packet, the receiver identify the congestion in the network, and this congestion signal is sent to the sender by the receiver. See, this dotted lines is the congestion signal is sent by the receiver to the sender. After receiving the congestion signal from the receiver, sender throttles back. It slows down its transmission because already here the router is in congestion. Okay? This is the explicit congestion notification. Okay, hope you understand, students. See, that is explicit. First one is choke packet. Second one is choke packet is the packet. In the explicit congestion notification, there is no generation of new packet. Just it's simply marked or tagged a packet which and forwards to the destination. And the third method is back pressure. This also we have discussed in last class. See here, source and destination we are having. Here, router 1, router 2, 3, and 4. Here, the congestion occurs at router 3. In the choke packet, there is a direct information passed to the source. From congested router, the information is directly passed to the source. In this back pressure model, here the congestion occurs, it will intimate it to the previous router, it will intimate it to the previous router, and it will intimate it to the source. Okay, this is the method of back pressure. Okay, this is one way of giving a feedback. Here, these three methods: choke packet, explicit congestion notification, and the back pressure. These three are giving a feedback to the sender. This is the hop by hop back pressure, right? This is hop by hop back pressure. This is normal back pressure. Next topic, this is hop by hop back pressure. Here, as high speeds are over long distances, many new packets may be transmitted after congestion has been signaled because of delay. What they're saying is, just understand, students. Here, the congestion occurs here. This notification, the congestion notification, has been sent to previous router, and it will send to the previous router, and it will send finally to the source. It will take some time to receive the information of congestion to the source. Okay, during this time, the source does not stop its transmission, but it continuously transmitting the data. Okay, what they're saying is, if it is a long distance, that means let us take an example. Let us it is the router number 3, right? It is router number 100. It will take one step. It will take more time to receive the congestion signal to the source. In those cases, what they are saying is, at high speeds or over long distances, many new packet has been transmitted after the congestion. Why? Because the delay before the signal takes effect. It is the delay. Consider, for example, a host in San Francisco. One host is in San Francisco, router A, the figure. That means the router A in the figure, the host is in San Francisco, that is sending the traffic to a host in New York, router D. San Francisco is router A, that is New York is router D, at the OC3 speed of 155 Mbps. Okay. If the New York host begins to run out of buffers, it will take about 40 milliseconds for a choke packet to get back the San Francisco. That means sender is at San Francisco, the receiver is at New York. Okay, the receiver is at New York, finds the congestion, and the New York host begins to run out of buffers. Run out of buffer means it cannot buffer the incoming packets. it will take 40 milliseconds. It will take 40 milliseconds to send that information through choke packet, get back to San Francisco. Okay. See, I will show you in diagram. See, these are the choke packets. Examples of showing slow reaction. The solution is hop by hop choke packet. See here, A is the source which is at San Francisco. D is the destination at New York. A to E, E to F, F to D. It will take more time. See, for a, this is a heavily flow. This is a heavy flow. Next, congestion occurs at D. That means D cannot able to buffer the incoming packets. So it needs to send choke packet. It needs to send choke packet. Next, in the next step, the choke packet up to this hop, the choke packet next step, and the next step, the choke packet is here. Friends, are you getting my point? See, A is the source that is at New York. B is the destination. A is the source that is San Francisco. D is the destination that is at New York. Okay. D is unable to buffer the incoming packets. That is the reason why he sends a choke packet to next one. That is the previous route. In the step, the next one. In the step, next one. That means D to F is the first choke packet. F to E is the second choke packet. And see, F2E is the second choke packet and E2A is the next choke packet. Okay. After receiving the choke packet, what the sender will do? What the sender will do after receiving the choke packet? It will reduces the flow. It will reduces the flow. Okay. Now, after reducing the flow is still at maximum rate. Flow is still at maximum rate. That means we have some flow of data. After getting the choke packet, the receiver slows down its transmission. Still the flow is maximum rate. Again, what they will do? Flow is reduced again. Next, heavy. If there is again heavy flow, that is reduced flow. There is a heavy flow. The choke packet is sent again. The choke packet is sent back. The choke packet is sent back. Okay. This is the way of having choke packet is sent. That means, suppose what happens is, what is the advantage of hop by hop back pressure? Students, just come back. Only you can see first diagram. A is transmitting packets to router E. Router E is transmitting to F. F is transmitting to D. What from which router D is getting the packets? From router F. The congestion occurs at router D. It intimates to the router F. Then what it will do? Router F slow down its transmission and again back pressure hop by hop. It intimated to E. Then E slow down its transmission. Next, what E will do? E will intimate to A. A slow down its transmission. That is the advantage of hop by hop back pressure. Hop by hop back pressure. Hop by hop choke packets. See here. The choke packet, the hop by hop back pressure. The choke packet propagation is illustrated as the second, third, and fourth steps in the figure. See here, second, third, and fourth steps. In the second step, the choke packet is sent from D to F. In the third step, choke packet is sent from F to E. In the fourth step, the choke packet is sent from E to A. In these 40 milliseconds, another 6.2 megabits will have been sent. Even if the host in San Francisco completely shutdowns immediately, the host in San Francisco shutdowns immediately, the 6.2 megabits in the pipe will continue to go and have a tilt with only the seventh diagram. See, see, 1, 2, 3, 4, 5, 6, seventh diagram. The flow is reduced. Only in the seventh diagram, the New York router notices the slower flow. New York router is nothing but is a destination. It finds a slower flow. That is slower transmission. An alternative approach is have the choke packet take effect at every hop it passes through, shown in the sequence of figure B. These are two figures, right? It is the first figure and it is the second figure. In the second figure, what they are doing is choke packet is sent. See, in the second figure, choke packet take effect at every hop and it passes through. Here, as soon as the choke packet receives F is required to reduce the flow at D. Doing so will require to F to devote more buffers. That is what I am saying. See here, in the step A, D congestion signal reaches to A, then only A stops its transmission. In the second diagram, D signal is reached to this F. F slows down its transmission and F is intimated back. Then it slows down its transmission and E is intimated back and A slows down its transmission. Okay, this is the advantage of hop by hop choke packets and back pressure. The next one is load shedding. When a router becomes inundated with packets, it simply drops some packets. Okay, load shedding means the meaning of this point is whenever the rotor is congested, it will simply drops some of the packets. Okay. Here in tomorrow's class, I will continue the topics, the load shedding and the traffic aware routing. Mostly tomorrow in first 10 to 20 minutes, 10 to 15 minutes, the topic will be completed. And tomorrow we are going to start our last unit, that is the 6th unit. Thank you, students.